Section 15.1, vector fields, is going to draw upon some of the things that we learned in Calc 3 with vectors. And to start with, I want you to imagine the idea of a vector field. So the basic idea, you guys know what vectors look like. They kind of look like arrays, like from geometry, right? They've got direction and they've got magnitude. Magnitude is the length, and then direction, of course, is the angle, basically, that they're occurring at. And we're going to have an entire field of them. So the idea is that you've got some kind of an image where there's vectors all over the two-dimensional or three-dimensional space. Now I'm not going to deal too much with the three-dimensional space ones simply because they're very difficult for us to visualize and difficult to draw, but they're very practical. So for example, if you're wanting to know about how wind goes around the wing of an airplane, that would be a three-dimensional vector space, right? And the wind would be the direction the wind is taking in the different directions and speed of the wind. So that would be a three-dimensional vector space. We're going to work more in the two-dimensional space because it's easier to get our hands on. And what I'd like for us to do first is to sort of formally define what a vector field is. We are going to define it in terms of three-dimensional space and two-dimensional space, however. So this is definition 1.1. A vector field in R2 is a function capital F. It's a vector function, okay? Capital F. I guess I had more space over there than I thought. Let me try that again. That takes a point, okay, an ordered pair xy, from two-dimensional space, right, R2, into V sub 2. And V sub 2 is a two-dimensional vector. So we're going from the plane into two-dimensional vector space. So every point is going to correspond to a vector, a two-dimensional vector. So far, so good? And you'll see we're going to draw some. We'll draw at least a little bit by hand before we start working with images on the computer. Or on the, I'm going to do it on the iPad, but you can do it on the computer too. So what this does is it actually takes a point, xy, and it takes two functions, f sub 1 of x, y, f sub 2 of x, y. Or we can define it, of course, with the ij notation. And turns them into vectors. So we've got two vectors coming out of 1 point. Not two vectors. I didn't say that right. We've got a vector coming out of 1 point with two direction, of course, to it, the x direction and the y direction. And this is for scalar functions f sub 1 of xy and f sub 2 of xy. This is in two-dimensional space. We can do this in three-dimensional space, and the definition looks almost identical, except what's going to happen, generally speaking. Can you give me some description? What do you think? We're going to have a z, right? We're going to be taking something, we're going to have a third dimension basically with it, right? We'll be also taking it from R3 into V3, that kind of stuff. So I'll write it out formally just so that you have it in your notes. So in R3, a vector field is a function f from xyz, just like you guys said, going from R3 into V3, which is a 3D vector space. And formally defined, this is taking f of x, y, z to the vector f1 of x, y, z, f2 of x, y, z, f3 of x, y, z, or we can use the alternate notation with I, j, and k. And just like on the last one, this is for scalar functions. F1 of x, y, z, f2 of x, y, z, and now also f3 of x, y, z.
Confused on the notation. So if f1, f2, and f3 are scalar functions, wouldn't that be 4 dimensions then? This x, y, z?
Okay, ask me one more time, Caleb.
Well, so for the scalar functions, f1, f2, and 3,
Yes.
since it's a scalar function but it has 3 variables, wouldn't that make it 4 dimensions?
It's 3 variables only in the sense that it's an ordered pair. The input is a point. So the inputs are not single values. The input's a location in space. I may not be answering the question in a way that's
Well, no, it's just
quite what
when
you're
it's the
asking.
scalar function, I mean, it makes me think of function, so it's a function of x, y, and z, so it would be a 4-dimensional thing, but it's okay.
Okay. Let's do an example of how we would graph one by hand. You're going to do a couple of these where you graph by hand. And then we'll take a look at what it looks like in a broader perspective using technology. So we're going to sketch the vector field by hand. Normally I'm a big fan of doing things by hand. I'm not a big fan of doing this particular one by hand, and you'll find out very quickly why, okay? So let's take a look. The function that we're going to use for the first one looks like this. Negative of x minus 1 I hat plus y minus 2 j hat. And if you want, I don't know why they write it awkwardly like this, we could certainly write this as 1 minus x I hat plus y minus 2 j hat, which might be a little bit easier to just not having all that negatives in case. Is that okay? All right. All right, to do this by hand, what we want to do is we want to pick different locations in two-dimensional space. Now, if you think about your two-dimensional space, in two-dimensional space we have, in fact, you know what, let me put it in here this way. I will change this out. I say I will. It's not doing it. No, it did. Okay, we'll graph it over here. Got ourselves a grid. Maybe I could get a bigger grid. That's a little bit easier to work with. And in 2 dimensions, we have 4 quadrants, of course. And we'd like to know something of what's happening in all 4 quadrants. So as we're choosing input points for this, we do need to make sure that we've got some input points in all locations. Also locations sort of along the x and the y axis. Everybody good so far? So we want to make sure that we're not picking, for instance, all x and y values that are positive. That wouldn't give us a whole picture of what's happening. Now, unfortunately, we're not going to get a very good whole picture of what's happening anyway, because we're only going to be picking a few points if we're doing this by hand. Do you already see the problem? Okay. So coming over here, we're going to create a rather, I don't want to use the word massive, but a rather detailed table. I'll go with 4 columns for now. And what I want in one of these cases is I want the ordered pair I'm picking. In the other case, I'd like to have, or in the other column, this is just a magnified 2 columns, but I don't have enough space to keep going. I'd like the vector that gives me. So again, this one will be the ordered pair, and then this is the vector that gives me. All right, so for instance, if I want to start along the positive x-axis, I might pick something like 2, 0. So if I plugged 2 in for x, what would be the x? And it happens to be that the way that this particular function is defined, x is only going in for the x component, y is only going in for the y component. That certainly wouldn't have to happen. But if I plug in the point 2, 0 into this function, what is the x coordinate of my vector that they give me, the first coordinate? -1. And how about the y coordinate? -2. All right, so over here on my graph, at the x, y point 2, 0, which is here, I need to draw a vector, and the vector needs to be going in the direction of -1, -2. Having magnitude, well, and because of that direction, I actually can see what I'm going to be. I've got to go left -1 and down -2. So I end up with my vector looking something like this. Is that okay? Okay. As far so good? Let's try some more of them. Somebody pick me a coordinate, and I'm going to go off of what I'm not going to take what I've got. You guys are going to pick for me. Pick me something in quadrant 1. Don't make the values too huge or we're going to get out of our picture of our graph. But something 1, 1, okay. 1, 1. All right, let's insert that. What would that give me for my x, for my first coordinate, my vector? 0. And my second one? -1, right? So at the ordered pair 1, 1, which I'm right here, I need to be going how? What's it going to look like? Just down 1? Okay, so looks good. All right, we're just going to kind of go, we're going to go counterclockwise around the circle. Somebody give me something along the vertical axis on the top.
0, 2.
0, 2. All right, if we do 0, 2, what vector will that give me? 1, 0. All right, so at 0, 2, I'm right here. Where's that vector going to point? Right 1, yeah. Just feel awkward to you? It looks very strange, doesn't it? Huh? It feels pointless. We're going to get one in every quadrant, and then we're going to broaden our horizons a little bit. How about in quadrant 2? Negative, what'd you say, Tally? -2, 1. All right, so if I put -2 in, what does it give me? Just 3? Okay. And then put in 1? -1. Okay, at -2, 1, right here, I'm supposed to be getting 3, -1. So what does that look like? Where will that point to? What ordered pair will that end at? It's going to end there, right?
So are these points we're pointing at, or just kind of an area? Because I know we're not making it.
It's the length and the direction.
Okay.
We'll talk more about what some of the applications are of what you're looking at in just a second. Okay, how about along the negative x-axis? Negative 2, 0. Why not? All right, negative 2, 0. What does that give me? It's still 3, right? And then negative 2. Okay, so we start out here. 3 and then negative 2. Where will that be pointing? Right here. Okay, how about quadrant 3? Okay, negative 2, negative 1. If you're picking negative 2, we've still got 3. I don't have to change that each time. And then how about negative 1? What is that going to give me? Negative 3. Okay, so negative 2, negative 1, and I get 3, negative 2. So is that here? Oh, was it negative 3?
Yeah. 3 negative.
3, negative 3. Oh, thank you. All right, so 3 and then negative 3. Things do seem to be pointing to the line x equals 1, right? So that is something that we can notice on this graph. I have just a couple more things I need to pick. I need to pick along the negative y-axis. So give me a point along the negative y-axis. I think you mean 0, negative 1, right, Jordan? Okay. So if we pick 0, we get 1. And negative 1, we get negative 3. So I'm right here, and then I'm supposed to be getting 1, negative 3. Hang on. That's the same location I got just a minute ago, isn't it?
Yep.
Okay. And let's pick something in the quadrant 4. 2, negative 2. Okay, so 2, negative 2. We've already picked 2 a couple of times, haven't we? At the beginning, so that's negative 1. And what happens when I use negative 2? So negative 4. Excellent. So 2, negative 2 starts here. And I'm supposed to be getting negative 1, negative 4. I think I'm off my screen, unfortunately, but we'll give a best picture we can from what we can work with. That look okay? Maybe I didn't get that right. Did I? Yeah, I did. Negative 1, negative 4. Right, it's close to down here, right? This feels very incomplete, at least it should. It should feel very incomplete to you because we've picked sort of some random points. We've got some sort of sense of there's this sort of tendency to end up along this axis of 1, but also maybe that's because of the points we picked, right? It's kind of hard to see that that's for sure happening. And what about all those other points? I mean, like, I can't pick every single point. I can't draw these vectors all day long, right? That's just not, practically speaking, going to happen. So I'd like to show you some technology kind of things to give you some perspective of what you can do. So this is what the expectation is when it says graph by hand. Let me just say that first. So when it says graph by hand, you're looking to find at least one point in each quadrant and along each of the axes, each compartment of the axes or whatever, okay? Is everybody good with this so far? All right. Okay, so from this picture that we get of the vector field and a more thorough picture when we look at the technologies vector field, which kind of fills it in more thoroughly for us, you might be looking at it and saying, okay, but what does that tell me, or how can I use that kind of information? And of course, it depends on the application you're looking at of the vector field. But the idea is that the velocity of any particle at point xy in the stream can be described by a vector field. F of xy. Okay, we already wrote all this down once before. This is two-dimensional, of course, because that's what we're working with at the moment. And we can use the velocity field. I'm sorry, the vector field. To construct flow lines. Which indicate the path followed by a particle starting at the given point This is found by dy dx equal, or set equal to, solving this anyway, f sub 2 of xy over f sub 1 of xy. I'll put the other phrase that I just omitted before over here. It's solutions to this equation. So I'm going to do kind of a two-part question. Your book kind of splits these apart into two questions themselves in the homeworks that you're looking at, but I'm going to kind of combine them. We're going to do a graph where we actually draw some flow lines, and we're going to do a graph where we find an equation of a flow line as well. Okay? We're going to do both those things. Did everyone get that written down? I'm sorry, I probably... Okay, good.
I think we did do a little bit of this in Cal too, actually.
Did you really?
We did directional field.
Okay.
I mean, it's similar.
Yeah.
Yeah, it was only for like one section.
One section. Awesome. Okay, well that's good. All right, so we're going to do an example. We're going to sketch the vector field. And as long as the book doesn't tell you by hand, I'm fine with you using the electronic version of doing something with this, okay? So sketch the vector field. And I think I only had you do 2 of them by hand, so it's not going to be a lengthy part of that assignment. And then we're going to sketch flow lines. I'll say this is sort of part A. Sketch flow lines. And we'll say part B is to find equations for the flow lines. And the equation we're going to do for this one, or the vector equation, is going to be 2 cosine x. All right, so this is what we had using the website that we were at. And the flow line means starting at one of these locations and following the curve. So we can draw several of these. I'll make mine a little bit thicker. And we're just following the basic curve that we're seeing happen here. And I might not be following it exactly, but you've got, yeah, I'm swiping everywhere, aren't I? That was bad. Let me turn my screen a little bit more straight for myself. Yeah, it's like connect the dots. Go with it. I'm not connecting dots very well.
I don't think that works. Good enough.
Oh, I didn't. I even disconnected it there, didn't I?
Good enough.
Do you understand basically what we're doing now? All right. And we can draw multiples of these things. At least if we're accurate, we could do better. But they won't necessarily. This one, they are sort of parallel, swooping lines. Do you know why? I mean, why is that happening on this one? Part of it's cosine. There's something else, though, too, that happened that was different. The 2. The x value didn't change anything, right? I mean, the vector, the first component of my vector is constant, which means my flow lines are actually not changing. So this is giving me sort of just stacking up different things. I mean, it's just a bunch of y equals at different heights of where x is, basically. Okay? So this is what we would do when we're asked for flow lines. So this is sort of part A of this direction, sketch flow lines. So you're going to sketch 2 or 3 of these things. Okay? Especially if they do end up being different on the graph that you're looking at. It might be that you have one piece of the flow lines where it looks circular and other pieces where it looks sort of like a parabola around the circle or something like that. So they wouldn't have to be sort of concentric circles necessarily or something. It doesn't have to be sort of parallel images sort of, at different levels away from it or something like that. This is not a level curve, although it does have some sort of a feel of that a little bit. The equation in the flow line. So that looks like a little bit more like calculus. At least in terms of writing out calculus as we've been used to doing. So what we'd written down on the slide before is that this is dy dx. It's the solutions to dy dx over f equals f sub 2 of xy over f sub 1 of xy. So we've got my dy dx. And f sub 2 of xy is what in this problem? It's the cosine right here. F sub 2 occurs second, f sub 1 is first. So this is cosine of x over 2. These will always be what are called separable differential equations. Now that is something you did in Calc 2, but you didn't do very much of it, and we will do more of it later this semester as well. So what does it mean to be separable differential equations? It means that I can separate these with all the x's on one side and all the y's on the other side. And that's what I want to do. I want this to be, cross-multiplied is the word that you guys are probably most familiar with or comfortable with. And you'll notice in this particular one, it very cleanly becomes what you want. If you ended up with the variables not working out already automatically, you would move them until they did. Like let's say, for instance, this ended up giving you 2 over x dy. Well, you just multiply the x to the other side, right? So you could still manipulate this, but you want all the x's on one side and all the y's on the other. And then do you know what you're going to do next?
Integrate.
You're going to integrate. Very good. So our goal is to find an equation of this, not a set of dy dx's, a differential of this. So the integral of 2 dy is 2y, and technically it's plus c, but we're just going to put the c on one side or the other, so I'm just going to put it on the other side when I'm done. Okay? Because if I put a C1 on the left and a C2 on the right, then I'm going to combine them anyway. There's no reason to put that on both sides. How about on the right-hand side? Sine x, and then plus c. Correct. And if you want to divide by 2, more power to you. Your book actually leaves it at this point, and I'm fine with that too since they are. Okay? So this is the equations for the flow line. And you can see with the plus c what's happening. That's why we get the different levels just up and down from where we are, right? Yeah. So this is just the equation y equals 1/2 sine of x plus a constant. Yes?
So sketching the flow lines, you just want us to look at that graph and kind of mimic it?
Mm-hmm. Yeah, that's what you're doing. Yeah, and you'll see pictures in your book doing the same thing. So.
Did you want us to like draw the arrows and then trace it, or just trace it?
I don't really want you to draw the arrows. I'd rather you just print them from the computer
Okay, so-
and then draw that. So the image, like if you think about this particular graph where we did the red arrows, you're actually getting that from a technology device,
So you
and then
want
your
us to print
flow
it?
lines. Yeah,
Okay.
print it out. Yes, please.
So you don't want us to draw it?
The only ones that I want you to draw are the ones that have the directions like we had over here that said, I think I skipped it, where to go. Yeah, where it says by hand. And I think there's 2 of them that I assigned that are by hand. And you can verify that with a technology device, but that one, the expectation is that you get your hands a little bit dirty. Okay?
So you want us to print these off?
Yes,
Turn it
unless it says that it wants you to do it by hand, you can print them off. Sound good, Jordan?
Yeah.
All
I just
right.
wanna be sure.
Will we print stuff off for the test?
We will figure out how to handle the test situation when we get there. We're still a little ways away from that, but we'll do something like that. I wouldn't expect you to do something in a testing environment you didn't do on your homework, okay?
Yeah.
Maybe we could. We can see. All right? What I'm more likely to do, and this is just me thinking off the top of my head, hey, Nathan, this is just me thinking off the top of my head. I think I would probably be more likely to say, here's 4 different, like give you a multiple choice kind of thing and say, here's 4 different graphs. Which one is the appropriate graph of the flow lines, or not flow lines, of the vector field. So you have to use a little bit of the by hand kind of thing in there without actually doing it by hand because it's tedious and it takes a long time. And then giving you kind of a graph where you say, now draw 3 flow lines of this particular graph. That's probably what I'd be more likely to do so that we don't have to actually have the technology in here to print it off at the same time. Again, that's just thinking off the top of my head, but I think that's probably what I would do. All right. All right, let's see where we were now. Okay. Something we've seen before, coming back at us again. An important, let me say that right, type of vector field. F looks like this. Do you remember we've seen that notation before? Or what we called it? It's a delta. It's gradient, right? It's a gradient. So this is actually called a gradient field. So let's actually formally define it now. So this is definition 1.2. For any scalar function f, the vector field that we just defined above is called the gradient field. For the function f. We call f a potential function. This is small f. For capital F, gradient f, this one right like this, on a region R, hang on, I think I've totally botched up something I wrote down. Just give me a second. All right, I did. I got off on a line. No wonder it doesn't make any sense anymore. After potential function, we stop there. And then I'll finish what I was writing before. I'm sorry. We call little f a potential function for capital F. Then we go with whenever the vector function capital F equals the gradient function little f on a region R, for some scalar function f, we say that, it's my capital F again, is a conservative vector field. On R. I'm not sure the history behind that language particularly, but that is the name for it. We're going to do a couple of examples with some gradients now, okay? Does everybody have this jotted down? Good. Okay. All right, so first example of this, very straightforward. We're going to find the gradient field. Corresponding to F. So f of xy is going to be the natural log of x squared plus y squared. The first thing to remember, since it's been a couple days since we've looked at this at least, is what do we mean when we say gradient function? Do you remember?
It's a vector and it's f sub x, right?
Yeah, okay, I'll use your notation, yeah. F sub x
That's the one.
and f sub y. Or you can write delta f over delta x, delta y over delta x. So you also could see the notation written like this. I still, even as I said it wrong, and then I wrote it wrong too. Either of those notations we've seen before. All right, so looking up at the particular function that we're dealing with, what would f sub x be? Just for fun, we'll write it over here, and then we'll put it in. You can certainly put it in straight away. But what would f sub x be?
2x divided by x squared plus y squared.
Okay, so the x squared plus y squared is in the denominator because of the natural log, right? Why is there 2x in the numerator?
Derivative, chain rule.
Chain rule, yeah, derivative of the inside. Yeah, good. And then f sub y would be, well, almost the same thing, right?
2y.
Yeah, 2y over x squared plus y squared. You can do this separately like I did. I was about to do it all at once as well, or you could just put it in straight away from here. Obviously, if you had more sort of simplifying or cleaning up to do, you might want to wait to put it into here until you've done that. This one doesn't require any, so it's not a big deal. But this is it. That's it. There's nothing else to do. Okay. So that's pretty straightforward, right? Okay. All right, so let's do something a little bit more interesting then. You will do a few of those that are very uninteresting, of course. But we're going to determine whether or not the vector field is conservative. On R2 or R3, and that just depends on the function you're working with. And if so, that is, if it is, we're going to find a potential function. All right, so the vector we're going to be working with is x minus 2xy I plus y squared minus x squared j. So the first thing we're going to do is we're going to find the gradient. Anybody want to help with that? What would the gradient of f be?
The whole thing.
Well, give it a try. Get us started. What do you think it would have for us, Jordan?
1 minus 2y.
Oh, I'm sorry. I left out one step before this. Oh, I don't need to erase this. I just need to move it down. I'm sorry. No wonder you guys are staring at me funny. I didn't write this piece down. Oh, I could write it in here even. That would be even better. Whoops. This piece is this, and this piece is this. And I'll go back to the definition so you can see what I'm doing here in just a second. But that is the gradient. The gradient is the function we're working with. Okay. Our goal is to find f. Gradient of f we're given. So let me go back to the definition real quick so I can show you wherever it went. There it is. What it says is whenever the function f equals the gradient of f on a region for some scalar function f, we say that f is conservative. This is one of those things where, like at the very end of those directions, it says, if so, find a potential function. This is one of those cases where we are attempting to find a potential function, and if it works, it's conservative and we found it, and if it doesn't work, then it can't be done. You guys have experienced that before, right? Where they say something like, do the lines intersect? Are they parallel? Are they perpendicular? What you do is you look to see, well, okay, if they intersect, it's going to be by this method. And so I'm going to try this method. I'm going to use matrices or something like that. And if I find an intersection, then the answer is they intersected. If I don't find an intersection, then the answer is they don't intersect. They're parallel or something like that. Okay? So our goal is to set these equal and look for this function f and see if it exists. So our function that we're starting with, oops, wrong one, is actually set equal to these pieces. So we have x minus 2xy and y squared minus x squared. So in particular now, the f of xy that we're looking for to see if it exists is going to be found by integrating. And we're going to do this one piece at a time. Maybe I should make mention of that. We're going to do this piece first. This will be the integral of x minus 2xy dx. What's the antiderivative of this with respect to x? We'll get to the other piece in a minute. Y'all are great at doing integrals now with lots of variables inside of them.
Squared over 2 minus x squared y.
Yes, it is plus c. We're going to write it as a function, g of y. It is a constant c. We'll see that come about in a minute. But in general, it could be a function. So this was done f of x, y. What I'd like to do is I'd like to take this function that I'm proposing exists and has this form, and I'd like to do its derivative now with respect to y. So just keep bearing with me, and we'll see what happens as we go, okay? If I take this derivative, this function over here, and I take its derivative with respect to y, what do I get? Somebody-
X squared.
Negative x squared, right? Negative x squared, and then what?
Plus g prime.
Plus g prime of y. And the reason we wrote the constant over here that you guys were telling me is a constant is g of y is because if it were a function in terms of y, it would still end up giving me a 0 if I took its derivative, right? So, because we were doing it with respect to x to begin with, right? Yes, this is g prime of y. Compare that now to df dy. Do we have df dy? Well, sure we do. It's right here. So df dy is actually, we know for a fact, y squared minus x squared. Well, what does that tell you from this description here?
G prime is equal to
G prime is equal to y
y squared.
squared. It's possible to do this, is what that tells you, right? The other pieces match up. The part that's not matching is g prime of y, which is negative x squared. And if that's g prime of y, then what's g of y?
You mean G prime y is equal to y squared?
Oh, did I write the wrong one down?
Right.
I sure did. I'm sorry. You're right. I apologize. Thank you. G prime of y is equal to y squared, yes. So what's g of y then? 1/3 y cubed. I'm waiting.
Plus C.
Thank you. Plus c. That's what I'm waiting for. You got it. Plus c. And I really need it to be plus c this time, like plain old constant. I don't have this in terms of x or y because I've dealt with both of them now, and I don't have any other extra pieces I can match things up to. This really is plus c. So what does that tell me? Well, it tells me this function that I almost found completely up here, right here, is right, except for the g of y that goes in the end is 1/3 y cubed plus c. So in particular, I've now run out of space officially over here. I had f of x, y. I had the x squared over 2. I had minus x squared y. And then in place of the g of y at the end, I have 1/3 y cubed plus c. And since I was able to actually find the f and it satisfied all the conditions, that means it's a conservative field. So the vector field is conservative.
So is the g of y, that's the potential function?
Let me see, hang on just a second. No, f is the potential function for f. It's just that because we were actually able to find it, it actually satisfied it.
What would
So-
make it term we couldn't find it?
Then it was a potential function that didn't work,
Okay.
right? It's like saying, I have a potential solution for your problem, and somebody says it, and you're like, I don't like that solution. It's not going to be your solution, right? And I mean like real life problem. The language is still the same. Yeah. So the field is conservative. The function that we actually found was correct. The potential function actually worked, and it was this function. So this f of x, y is the potential function, and it works for what we're doing.
So if it's conservative, to find out if it's conservative, we have to find a potential function that works.
Exactly.
Okay.
Yeah. Now, what would have happened if we had gotten to, say, this point right here, And instead of getting y squared minus x squared where the pieces matched up, right, like this one, it matched this one, and we were actually able to identify g prime of y, and it actually is in terms of, if that all works, then you've got your potential function, everything's good. If you ended up with something here that doesn't work, that's when you're going to run into problems.
So if it's like g prime y equals x squared.
Yeah, then we would have
So if
problems.
it's not conservative, you're gonna end up stopping about right there.
Exactly. Yeah, you're going to end up with a problem coming up right there. Exactly. All right, homework. It's not my screen. This is page 987. Numbers 147. I think it's those first three, it may be three of them where you're going to do by hand the vector fields. After that, if they're dealing with vector fields, they want you to draw them. You can use your technology to do that. 1922. And that's all she wrote for today.